The final topic in SEA A2 Unit 1 is on aromatic chemistry. We're going to start this topic by looking at how we name some benzene-based molecules. In this topic, there is only one definition, and that is the definition for delocalization. When we name a molecule based on benzene, we add on the substituent as shown in the examples. For example, methylbenzene, chlorobenzene, nitrobenzene, and benzene carboxylic acid, more commonly referred to as benzoic acid. When there is more than one substituent, we have to use numbers. Here are a few examples: 1,3-dimethylbenzene, 2-hydroxine benzene carboxylic acid, and finally 3,5-dinitro-benzene carboxylic acid. When the ring is a substituent, it becomes a phenyl. We're going to meet phenylamine in Unit 2. It's also referred to as aniline. And in this topic, we are going to find reactions where we form phenylethanone. When we have an OH group on a benzene ring, the molecule is now named phenol. We can get aromatic compounds with more than one benzene ring. 2 benzene rings is referred to as naphthalene and 3 benzene rings as anthracene. Can you work out the formula of these molecules? Pause the video and have a go. Naphthalene is C10H8 and anthracene is C14H10. In the next section, we are going to look at the structure of the benzene molecule and compare the reactivities of benzene with alkenes. Benzene has a molecular formula C6H6. That gives its empirical formula as CH. It also has a molecular mass of 78. Calculi originally suggested that benzene was a planar cyclic molecule that had alternating double and single bonds. Let's recap what a pi bond is. We met pi bonds in the alkenes topic in Unit 2 of AS Chemistry. A pi bond is formed by the sideways overlap of 2 p orbitals. This gives rise to the planar arrangement around the carbon-carbon double bond. We say that the electrons are localized between the 2 carbon atoms, and we would see addition reactions with these molecules. In benzene, each carbon uses 3 of its outer electrons to form 3 sigma bonds to 2 other carbon atoms and 1 hydrogen. This leaves each carbon atom with 1 electron in a p orbital. The lobes of the p orbitals overlap sideways and the 6p electrons delocalize and give regions of electron density above and below the ring. It is the delocalized ring of pi electrons which gives benzene its stability. There is evidence that benzene has a delocalized pi electron system. The length of the carbon-carbon bond in benzene is between the length of a single and double bond. It does not undergo addition reactions readily, and hydrogenation of benzene is less exothermic than expected. When hydrocarbons with double bonds are reduced to the corresponding saturated compound, energy is released. If we look at cyclohexene, when we add hydrogen across a double bond, 120 kilojoules of energy is released per mole. If we think about having 3 double bonds, we would expect 360 kilojoules per mole of energy to be released. When we hydrogenate benzene, it only releases 208 kilojoules per mole of energy. This is less than we expected, and this suggests that benzene is more stable than we expect. In the next section, we are going to look at the mechanism involved in benzene reactions, which is electrophilic substitution. It is important that you know your definition for an electrophile on your AS glossary. An electrophile is an ion or molecule that attacks regions of high electron density. Let's look at the mechanism for electrophilic substitution. In the first stage, The high electron density of the delocalized ring of electrons attracts the electrophile, and a pair of electrons from the ring of delocalized pi electrons forms a bond with the electrophile, breaking the electron ring. At this point, we have a highly unstable intermediate, which has only a partially delocalized electron system, and now contains 4 delocalized electrons instead of 6. That is why we have the full positive charge on the intermediate. In the unstable intermediate, the carbon-hydrogen bond breaks and the 2 electrons in the bond move back into the pi system, reforming the stable delocalized electron ring with its 6 electrons. The hydrogen is lost as an H+. The first type of electrophilic substitution we are going to look at is monobromination. In monobromination, one of the hydrogen atoms on the benzene ring is replaced by a bromine atom. Unlike alkenes, benzene is too stable to start to react with bromine on its own. However, it does react with bromine in the presence of a special type of catalyst called a halogen carrier. The halogen carrier catalyst is iron 3 bromide, or iron can be used as it will react with bromine to form the required iron 3 bromide in situ. The conditions for this reaction are room temperature and the catalyst of iron or iron 3 bromide. The electrophile in this case is the bromium ion Br+, and it is formed by the reaction of bromine with the catalyst. The H+ that has been produced at the end of the reaction combines with the FeBr4- to regenerate the iron bromide, so the catalyst is regenerated. Now that we have studied the reaction of benzene with bromine, let's compare that reaction with an alkene and bromine and compare the relative stabilities of the pi electron systems. Both alkanes and benzene have regions of high electron density. Alkanes have an electron-rich double bond, and benzene has a delocalized ring of pi electrons. Because of this similarity, alkanes and benzene both react with electrophiles. However, the similarity ends there because alkanes undergo addition reactions and benzene undergoes substitution reactions. If we look at the slide, we will see the addition of bromine to ethene. Alkanes react readily with bromine in an addition reaction. When bromine approaches an alkane, the electrons in the pi bond repel the electrons in the bromine-bromine bond, which induces a slight dipole in the molecule and makes it polar. The pi electron pair are attracted to the slightly positive carbon atom, and this causes the double bond to break. If we now look at benzene, benzene is resistant to addition reactions. This is because the electrons from the delocalized system would need to bond to the atom or groups being added, and this would disrupt the delocalized ring and cause the molecule to lose its stability. When a non-polar molecule such as bromine approaches the ring, the electrons are delocalized across 6 carbon atoms, and there is insufficient pi electron density above and below any 2 carbon atoms to cause polarization. This makes benzene resistant to addition reactions. Benzene undergoes substitution reactions. This is where one or more of the hydrogen atoms is replaced by another atom or group. The organic product formed retains the delocalized ring of electrons and hence the stability of the ring. Let's see, can you fill in this table? For benzene and the alkene, can you think about the electron arrangement, the type of reaction, and whether we use a catalyst? Pause the video and have a go. In benzene, we have the overlap of 6 p orbitals forming a pi delocalized ring. However, in an alkane, we have the sideways overlap of 2 p orbitals forming a pi localized bond. The reaction in benzene is electrophilic substitution, where the pi bond is not broken. However, in an alkane, the reaction is electrophilic addition and the pi bond has been broken. In benzene, we use a catalyst, for example, iron bromide, aluminium chloride. With an alkene, if you think of the reaction of an alkene with bromine water, you don't need a catalyst. The reaction is spontaneous. In mononitration of benzene, one of the hydrogen atoms on the benzene ring is replaced by a nitro group. If we have a look at the mechanism, you can see that the first curly arrow must come from the delocalized ring to the positive on the nitrogen of the electrophile. The second curly arrow must come from the middle of the bond into the hexagon. In this reaction, the conditions are concentrated sulfuric and concentrated nitric acid, and this is called a nitrating mixture, and the reaction must proceed at a temperature not exceeding 50 degrees centigrade. The overall equation for the reaction is shown below. The nitrating mixture is concentrated sulfuric acid and concentrated nitric acid. If we have a look at this equation, we can see how the nitronium electrophile is generated from the nitrating mixture. In this reaction, sulfuric acid is the stronger acid, so it is protonating the nitric acid. At the end of the reaction, the HSO4- ion combines with the H+ to produce sulfuric acid, so the catalyst, concentrated sulfuric acid, is regenerated. The next type of reaction we're going to look at is alkylation. Alkylation is the process of replacing a hydrogen atom in certain molecules by an alkyl group. It is sometimes referred to as a Friedel-Crafts reaction. Benzene reacts with a halogenoalkane in the presence of aluminium chloride catalyst to form alkyl benzene. How do we form the electrophile? We react aluminium chloride with the alkyl chloride and we produce our alkyl ion, which is the electrophile. The mechanism for the alkylation is shown. The catalyst is regenerated again in the following reaction. Acylation is the process of replacing a hydrogen atom in certain molecules by an acyl group. Acyl chlorides in the presence of a catalyst can be used to acylate benzene and form an aromatic ketone. The catalyst is aluminium chloride and the conditions must be anhydrous to prevent its hydrolysis. The electrophile that is formed is called an acylum electrophile. Again, here is the reaction mechanism and the regeneration of the catalyst equation. The final part of this topic is where we prepare methyl 3-nitrobenzoate from methyl benzoate to illustrate the nitration reaction. Nitrobenzene is not prepared in the lab due to the high toxicity of benzene. To illustrate nitration in the lab, we use methyl benzoate, which is an ester of lower toxicity. Methyl 3-nitrobenzoate is a cream solid. This is the practical details for the preparation of methyl 3-nitrobenzoate that you will find in the SEA practical guide. Be aware that you will be expected to know how to use a Buckner funnel in this preparation. In this practical, you could be asked to draw and explain Buckner filtration. You could also be asked how to recrystallize a solid and how to take a melting point. Here is a diagram of Buckner filtration from a past paper mark scheme and the explanation to how it works. We use Buckner filtration because it is faster than filtering using gravity and we also get a drier product.